Hello, my name is Dan Tempest, and today I'm going to talk to you about electrocardiograms and their correlation to cardiac events. So, to get started, I'm going to just talk briefly about what's really controlling what's going on here. And what we have here is a couple nodes, and the SA node is kind of like the pacemaker node. It initiates all of what's going to go on, and then, so that's going to trigger our atriums and specifically atrial contraction. And then that will be sent down to here. We have the AV node, which is going to cause contraction or elicit contraction of our ventricles. It does that by sending a message down through the interventricular septum and all the way around into the Purkinje fibers. Okay, so that's again what's going to really be controlling all this depolarization talk that I'm going to be talking about. If I talk about the electrocardiogram just as the basics of it, what we're doing here is we're recording electrical changes that are occurring in the myocardium. And that's going to be used to assess the heart's ability to conduct impulses. So just to kind of go through the basics of the image that you usually see, we have a P wave, which is going to be down here. That's going to be atrial depolarization. It's going to cause atrial contraction during that period. Then we have the QRS complex, which is our peak here, our largest peak. That's going to be ventricular depolarization, causing contraction or systole of the ventricles. And then eventually we reach our T wave, which is ventricular repolarization. All right. So if we look at a clinical application real quick, I just want to go into a couple things that we would do in trying to interpret an ECG. So one of the things that we would look at is a PR interval, and that's the time between the P wave and the start of the P wave and the start of the QRS. So here we have a P wave, and here we have a QRS complex. And in the timing wise, that should be between about 0.12 to 0.2 seconds of time in between those two, in between, again, that start of the P wave and the start of the QRS complex. If we're outside of that range, it could mean that somebody has an arrhythmia. Another example of what we could do is a QRS interval, and that should be between 0.06 and 0.12 seconds. So it's a little quicker than that PR interval. Again, if we are outside that range, which is what we see in this particular graph that we see here, we could have an arrhythmia. And so we have a prolonged QRS complex in this particular image. Another thing that we can use to interpret an EKG is just overall rhythm, such as what we would use in this case, it would be the distance between the R's. So we have an R here and an R here, and we can use that distance and we can, it should first of all be consistent if we have a regular heartbeat. And if we have an irregular heartbeat, it would be inconsistent. All right, moving on. So I have two images. I have this one, which is going to show really what's going on in the actual heart as far as like where things are happening. And then I have this image, which is going to go into a lot of the kind of the behind the scenes things, what's going to go on. So I'm going to go into this basics first, and then we'll go into the particulars of the other image. So if we look at this image here, again, looking at what's going on in the actual heart, at number one, we have a heart at rest. And then at number two, what we're seeing here is a P wave. The start of the P wave. And again, that's going to happen in our atrium. And we're going to have a depolarization in that atria. And that's going to cause atrial contraction, also known as systole. Blood will then pass through our AV valve and into the ventricles, causing an increase in blood volume in the ventricles. Then, if we look down here, we're getting into the QRS complex. And that's going to start at number 4. And in the QRS complex, we have a depolarization of the ventricles, and that's going to be quite large. You'll notice that the magnitude of that is a lot larger than the P wave. And that's simply because the ventricles are a lot bigger and larger in structure. So when this happens, this depolarization of the ventricles, it's going to cause ventricular contraction, again, also known as systole. Eventually, that contraction will get enough pressure on that blood to open the semilunar valve, and it will push that blood out and into the aorta and out of the heart. And that will be traveling then throughout the body. All right, now if we look down here, we're going to move into the T wave at number 6. And the T wave is when we have ventricular repolarization. The ventricles are going to relax, dropping ventricular pressure. And when that pressure eventually falls below the atrial pressure, the AV valve can then open, allowing a passive flow of blood into the ventricles. It's not going to be flowing into the ventricles because of atrial contraction at this time. It's just passive flow into the atria, just because we have that less pressure, allowing for that valve to be open. And this is going to continue until we reach another P wave. Okay, so that's that diagram. I'm going to go through this one, which again has a lot going on, but I think we can make this work. So again, just before I get into this, what I want to do is just kind of reiterate the overall cardiac cycle. What's going on here? We have blood entering the heart via the atria on both sides, the right from the body, the left from the lungs. We have the atria will contract then and push blood into the ventricles. And then when the ventricles contract, the blood will be pushed out of the heart, either to the aorta or out to the lungs. All right, so again, down here we have our electrocardiogram. That's the third part down. It all starts with the P wave, which is a depolarization of the atria. This is going to be caused by it's going to cause atrial contraction or systole. Again, contraction and systole are pretty much interchangeable, and that's going to cause atrial pressure to rise. And that makes sense because if you squeeze something, it's going to increase pressure. So if I go up here to this top, which measures pressure, we can see there is a slight increase in pressure. Okay, so the blood is going to pass through our AV valve into the ventricles, causing an increase in ventricular volume, which we do see right here. Ventricular volume is increasing, starting with that P wave. All right, now if we move into the QRS complex, we have a depolarization of the ventricles, and that's going to be, again, quite larger simply because it's a larger structure, and that's going to cause ventricular contraction or systole. Ventricular systole is going to go on now. And when those ventricles contract, the pressure goes up significantly. And we do see that up here. If we look, the pressure goes quite high. Now, you'll notice here it says aortic semilunar valve opens. And it opens right around that 80 millimeters of mercury. Now, that's a really important thing because that's about the pressure of the blood that is in the aorta. So we have to exceed 80 before that semilunar valve will open. But before this occurs, the ventricle is in what we call isovolumetric contraction because the volume isn't changing within it. However, it is still contracting. So that's why that pressure is just rising like crazy through that time. It's just because there's nowhere for that blood to go. All the valves are closed during that time. The valve doesn't open until we reach that threshold of 80, which is, again, what that blood is at in the aorta. So in order to push that blood into the aorta, we have to exceed that before the valve will open. When the valve opens, the blood is pushed out of the heart to the rest of the body, dropping ventricular volume. So we do see a drop here in ventricular volume at that time at the end of the QRS complex. Moving into the T wave. The T wave is right here. T wave is when we have ventricular repolarization. The ventricles will eventually relax, dropping ventricular pressure. We do see a drop in pressure during that T wave. The valves close, causing isovolumetric relaxation. And with this relaxation, ventricular pressure is going to drop significantly. Eventually, that pressure will fall below atrial pressure. And when that happens, the AV valve will open. So we see that here. The AV valve is going to open. And that's going to allow passive flow of blood into the ventricles through the atrium. And this would continue then until that P wave would happen again. We have another P wave happening down here. The last thing that's on this slide is the heart sounds, also known as a phonocardiogram. And again, that's the sounds of the heartbeat. And there's this classic lub-dub, lub-dub. And that lub-dub sound is coming from the valves closing. So the lub sound that comes first actually coincides with the QRS complex. And you'll see that here. Here we have the lub, and it's right next to the QRS complex. When the ventricular systole is occurring, and this closes that AV valve, resulting in the sound. As I mentioned, the sound really comes from the closing of the valves. So in this case, that first sound comes from the closing of that AV valve during the QRS complex. The second sound then comes from follows the T wave, and that's when those ventricles relax and the semilunar valves close, and that results in that dub sound. So you can see that dub sound right here coincides with the end of the T wave, which is when those ventricles really relax and the semilunar valve would close. All right, so there are other things that do impact heart rate. One would be exercise, body temperatures, certain ions like potassium and calcium can also, and also our nervous system, particularly the parasympathetic and sympathetic divisions, can also increase or decrease heart action. So there's other things that do impact the cardiac cycle. Another clinical application quickly, we can use these ECGs to diagnose, not exclusively, but we can definitely monitor them and look at and be triggered to these things through an ECG. Ventricular fibrillation is one that I'm going to look at in the lab or the journal article that I analyzed. And we can also have a rapid heartbeat and a rapid rate of atrial depolarization as well. So these are just 3 examples of arrhythmias, and that could be resulting from a cardiac cycle that is just abnormal or not working properly. All right, so the lab that I looked into was quite interesting. I looked at the ECG and this particular group of people did a research study on the app that is found on the Apple Watch that has it's called the ECG Detail app. And what it can do is detect AFib, or atrial fibrillation. And most of the findings are negative from this. I'll get into that in a minute. But the Apple Watch, again, they say can detect AFib, which can lead to a stroke. So if we can catch it early, people think that would be a good thing, right? So we could catch a stroke before it happens. No longer would you need to have an episode and be tested in a clinical setting. A positive of this, again, it could be a vehicle to introduce medical knowledge and practices to help healthy individuals before they have an issue. So that's a positive, right? However, clinics are quite skeptical about the efficacy of this, and they believe it's quite gimmicky, and there might be a lot of false positives that are quite likely from something like this. So these individuals did a study. The study was to examine consumer experiences and perspectives on this watch. So they did this via interviews. It was really a qualitative interview approach. They interviewed 19 individuals, all at different ages. They had 9 females and 10 males. So that was really our independent variable. We changed the ages and the people. And what they were measuring, their dependent variable, was the interview. What are the themes that came out of that interview? So one of the things that they found is the themes that came out were the values, the meanings, the possibilities, and limitations that consumers placed on this early disease detection device. So what did they find? The findings of this particular study were that consumers' medical knowledge and practices associated with the watch and the app on the watch were really shaped more from market agenda, because they want to make money, right? More so than expert judgment. And that really creates challenges because what essentially is happening here is medical overuse. People are analyzing things that really doesn't need to be analyzed. They really don't have any issues. There might be really rare circumstances where it could come in handy, but they are extremely rare. This really, they say, opens the floodgates for marketing more of medical monitoring devices, maybe new apps that would even show more stuff that may or may not be important. And that really is a challenge in the future to support more realistic expectations of the benefits of these monitoring and screenings and also the harms because, and I quote from this article or journal article that I read, they said more medicine is not always better. So we do need to remember that there always are limitations and nothing ever is perfect. So it might seem really fun to be able to watch your own ECG on your watch, but are we really getting good data is a good question to ask ourselves. And that here is my references that I used on this presentation. I hope you enjoyed, and that's all I have to offer for today. Take care.